Good afternoon. Just looking at what we have had for operations between functions, and on page 225, okay, now we have three given functions, okay, whereupon we have f of x is linear, okay, where this is set equal to negative 2x, and we have g of x, okay, and this is given in absolute value terms. Okay, where we have the absolute value of x plus 4, and then we have, with the remaining part of the trio, okay, so we have h of x, and this is going to be the reciprocal of x minus 3. Okay, so we have h of x is equal to 1 over x minus 3. And for what we have for the even numbered problems, we have for number 10, okay, we're looking at evaluating, okay, what we have in the difference function, whereupon we have g minus h of 2. Okay, so you have a difference function with g minus h, where the specified input is at 2. Okay, and so writing this as a difference of functions, okay, so this would translate to g of 2 minus h of 2. And we can specify, okay, just what those particular values are going to be. Okay, so we have, in the case of g of 2, okay, so g of 2, how do we get to g of 2? Well, we got g of x, where x is set to 2. And so g of 2 is going to be the absolute value, 2 plus 4. Okay, so you have 2 plus 4 is 6. And we have the absolute value of 6, okay, is going to be 6. And for what we have in the case of h of 2, okay, so h of 2, okay, so you have the h function, h of the input is equal to 1 over the input minus 3. Okay, so you have 1 over 2 minus 3. And 2 minus 3 is negative 1, and 1 over negative 1 is minus 1. And following through, okay, so for g minus h of 2, we got g of 2, okay, which is 6. And we have minus, and h of 2 we have at negative 1. So we got 6 minus negative 1, and this will translate to 6 plus 1. And so we have for the final answer, okay, that is going to be 7. Now for what we have in the case of number 12, and we're looking at, again, working with the g and the h function, and now we have posed the problem, okay, where we are looking at finding out what h times g of 4 will be. Okay, and so writing this product function as a product of functions, okay, we're going to have h of 4 times g of 4, and we can go ahead and evaluate h of 4 as well as g of 4. Okay, and for h of 4, okay, so this is going to be 1 over 4 minus 3. Four minus 3 is 1, and 1 over 1 is equal to 1. And for what we have in the case of g of 4, okay, so we have, again, absolute value function, okay, and with x at 4, okay, we have the absolute value of 4 plus 4. 4 plus 4 is 8, and its absolute value is 8. And so for the product function, h times g of 4, okay, so that's going to be equal to 1 times 8, and again, that is going to be at 8. Now for what we have in the case of number 14, okay, so we are now looking at working with the function f, and we have in this one, okay, we have f plus h of 5, and expanding on out. Okay, so this is going to be f of 5 plus h of 5, and looking at attaining the values of f of 5 and h of 5. Okay, so you have with f of 5, okay, we have f of x equal to negative 2x, so f of 5 is equal to negative 2 times 5. Okay, so this will be negative 10. And for h of 5, okay, h of 5, we have 1 all over 5 minus 3. And so we have 5 minus 3 is 2. And we have the h of 5 is equal to 1/2. Okay, so taking what we have now, okay, so f of 5 we have at negative 10, and h of 5 we have at 1/2, and combining the terms together. Okay, so negative 10, think of this as like negative 10 over 1, and negative 20 over 2 is going to be the equivalent of negative 10 over 1, but expressed in halves, and I can join with 1/2 finally. And negative 20 halves plus 1/2 will be equal to negative 19 halves, or negative 9.5. Okay, now for what we have in the case of number 16, okay, alright, so we have the interaction between f and h once again, and this time we're working with division. And now we have h over f of 7 and expanding on out. Okay, so the quotient function h over f of 7, we can expand this out as a quotient attained from dividing h of 7 by f of 7. And so we have with h of 7, okay, so we have 1 over 7 minus 3, and so this will be at 1/4. And for f of 7, okay, so you have negative 2 times 7, okay, which will be negative 14. So we have for h of 7, okay, so this is going to be 1/4. Again, we have all over f of 7. F of 7 we have at minus 14. And here, okay, so you've got 1/4 divided by negative 14. Okay, and if I divide by a number, it'll be the same as multiplying by its reciprocal. Okay, so just kind of expanding on out. Okay, so you have like 1/4 divided by negative 14. So say I have 1/4 times the reciprocal, okay, which would be negative 1/14, and a positive times a negative is a negative. So I have the negative of 1, and 4 times 14 comes out to 56. So h over f of 7 is equal to negative 1/56. Alright, now for what we have in the case of the next even item, and we have for number 18, okay, so we're looking at, in this we have h over g of negative 4. So we're looking at another quotient. Okay, so this comes down to h of negative 4 over g of negative 4. Then we have with the numbers. Okay, so we have with h of negative 4. Just have 1 over negative 4 minus 3. So you have 1 over negative 7, or negative 1/7. And as for what we have for g of negative 4, we have the absolute value of negative 4 plus 4. Negative 4 plus 4 will cancel. So we have the absolute value of 0, which is going to go to 0. Okay. And so for what we have in following through, so you got h of negative 4 is negative 1/7. So that is the numerator of this overall fraction. And for g of negative 4, okay, that is going to be at 0. And it is at this point that you can stop, because you have, for this denominator, okay, that is a 0 value. So it's going to turn out that for h over g of negative 4, this will end up as undefined. So there's no real solution in this one. Right. Now, for what we have in the case of the crossover, okay, to numbers 20 through 26 even, okay, now we are presented a different set of functions. And for these, okay, so we have with r of x, okay, so we have r of x, okay, is equal to x squared plus 3x, made that r of x equal to negative 3x. It is p of x that is presented as x squared plus 3x. And we have with q of x, okay, so q of x, okay, that is equal to the square root of 1 minus x. Alright, and just sort of laying the groundwork here, okay, because we'll be looking at domains in addition to the overall operational function results. Now, r of x, okay, we have negative 3x. Okay, so you do not have an even root radical or a fraction for r of x. So this function has no restriction. And for what we have in the case of p of x, so we have x squared plus 3x, no fraction, no even root radical. So this also has no restriction. Now for q of x, now we have the square root of 1 minus x. And in the real number system, we cannot have the square root of a negative expression. Okay, so we have, since we have the square root, okay, now we have that 1 minus x cannot be negative. Now it can be 0 and it can be positive. But we have the square root of 1 minus x presented in direct fashion. So we can have the square root of 0, which is 0, as well as the square root of any positive value. Okay. And so for what is allowed for 1 minus x, we have that it is greater than or equal to 0. And looking at what we have for the restrictions for x, okay, so if I rewrite this inequality in terms of just x, okay, so we take 1 away from both sides, and so we have that negative x is greater than or equal to negative 1. And looking at going from a negative to a positive x, okay, so again we're back to the scenario where if we multiply or divide by a negative for an inequality statement, again the direction will change. And so for what we have here, okay, so we have going from greater than or equal to less than or equal to, And so we're going to have the x is less than or equal to 1. Alright, and so for q of x, okay, for this function, it's going to have the restriction that x has to be less than or equal to 1. And now, crossing over into the threshold of working with operations, okay, among these three functions, and I'll just restate the individual functions and their restrictions, if any. Okay, so r of x is no restriction, p of x no restriction, but q of x, we have the x is less than or equal to 1. And for what we have in the case of what we have for number 20, okay, so we are looking at p minus r of x. Okay, so we had the input just non-specified, just given in terms of x. Okay, so you got p minus r of x. Okay, and just looking at what we have for these functions. Okay, so we're working with p of x as well as r of x. Again, neither p of x nor r of x will have any restrictions. And again, the sum, difference, and product functions will have their restrictions on the basis of combining the restrictions, if any, for the individual functions involved. Okay, so p of x and r of x have no restriction, and the same thing is going to apply for the difference function. And looking at what we have for p minus r of x. Okay, so we're looking at p of x minus r of x, and looking at what we have for the specific expressions. Okay, so p of x, we have x squared plus 3x. And we have minus r of x, and r of x we have at negative 3x. And so we have subtraction of a negative. I can translate this to plus 3x, and once I remove the parentheses, I have x squared plus 3x followed by another 3x, and so we have with this output, so this will come out to x squared plus 6x. And for what we have in the case of the domain, the domain of p minus r of x, okay, because there was no restriction for p of x or r of x, and thus no restriction for the difference function, it's going to turn out that the domain is going to be the set of all real numbers. And for the interval notation, again, we're going to have parentheses around negative and positive infinity. Now, for what we have working with these functions again, now we have crossing over to number 22. Okay, this time we're looking at multiplication between r and q of x. Okay, so you have for number 22. Okay, so you have with r times q of x. Okay. Now, in this particular case, all right, so r times q of x. Okay, now r has no restriction. However, q has the restriction that x is less than or equal to 1. And had to be able to work with both r of x and q of x. Okay, so r of x, I can plug in anything for x, but I had to work with q of x, so this time around I'm constricted to values less than or equal to 1 for x. Okay, so you have x is less than or equal to 1 because of the q of x portion. Now looking at what we have for r times q of x, and there's really not going to be that much to do here, okay, because translating in terms of the product of the functions r of x and q of x, so I have r of x times q of x. R of x we have negative 3x, and for q of x I have the square root of 1 minus x, and this expression is already in simplified form, or at least in terms of what as much as you can do, because I cannot distribute directly like x over the square root of 1 minus x. So I have a radical as opposed to parentheses around 1 minus x. Okay, so just filling in. So this is going to be the result for r times q of x, and we have for the restriction that x is less than or equal to 1. And it's going to turn out that for the domain of r times q of x. So if you were to envision like a graph with a solid point on 1 thanks to the equal sign and array going to the left, okay, the interval notation for this activity, you have going from negative infinity approaching and including the number 1, and the 1, since it is included, is going to be in the bracket. Now, where we have quotient functions involved, okay, now these are a little bit tricky because with quotient functions, again, some difference in product functions will have their domain defined by the restrictions placed upon the individual functions when put together. And the quotient function does consider that, but there might be another variable or discrepancy, okay, in terms of what is restricted. And for what we have in the case of 24, okay, this time we have the quotient function whereupon we have q over r of x. Okay, so for q over r of x, so we are involving q of x and r of x. Again, r of x has no restriction. Q of x, we have that x is less than or equal to 1. Okay, but now there might be an added restriction as we follow through with the division. So I'm just going to say that the restriction so far is going to stem what is imposed for q of x. So I'm going to stress this, okay, especially the so far portion, the restriction so far. Again, coming from q of x, okay, so you have the x is less than or equal to 1. And looking at how the quotient function here is going to play out. So we've got q over r of x, so that is equal to q of x all over r of x. Okay. And again, we have with q of x, we have the square root of 1 minus x. And r of x, okay, we have negative 3x. And just the mere substitution, okay, that is going to be our result for that particular quotient function. Now, looking into what we have regarding the restrictions. Again, the restriction so far, which we started out with, was with the q of x portion. Again, so to keep the square root of 1 minus x from having 1 minus x to be a negative. Again, x had to be less than or equal to 1. But now with r of x, there was no restriction upon r of x, but since we have it situated in the denominator, okay, it's going to turn out that we're going to have that negative 3x cannot be equal to 0. And if negative 3 times x cannot be 0, and we divide by negative 3, okay, well, we have that x cannot be equal to 0. Okay. And looking for the domain of this particular quotient function. So we have these, not just x is less than or equal to 1, but thanks to r of x being at the bottom, we now have the restriction added that x cannot be 0. So for the numbers of interest, okay, we have 0, and we also have 1. Okay, so we have x cannot be equal to 0. I'll just put a open circle over this. Now for x is less than or equal to 1, okay, 1 is included. Okay, so you're going to have a solid point. And had it not been for the added restriction that x cannot be 0, I would have had a ray going continuously to the left. Okay, so had this been the only restriction, I'd be going non-stop out to the left. But for what I have here, so I have starting going to the left, but I'm not going to have continuity because of the exclusion of 0. Thanks to r of x not allowed to be 0. Okay, so 0 is left out, but once I get past 0, I'm able to pick up and resume, finally with the ray going continuously to the left. Okay. And so for what we have here, for the limits, and placing interval notation, okay, for the domain of q over r of x. So we have at the lower end, okay, so you have between negative infinity and 0, but not including 0. So I have a parenthesis around 0, and then proceeding to the right, and we have bypassing 0. So we have values of x such that, okay, x is going to be greater than 0, and in turn x is going to be less than or equal to 1, and so that value is going to be bracketed. And so that'll be the interval notation for the domain of this particular quotient function. Right. Now, for what we have in the case of 26, okay, we have a role reversal in terms of what is in the numerator and what is in the denominator. And we have here, you know, we're working with r over q of x. Again, just looking at it up front, r of x, there's no restriction, q of x, you just have the x is less than or equal to 1. Okay, I'm just going to stress, because we're dealing with the quotient function, again, there might be a whole new dynamic added. So we have just the restriction so far. Okay, we have the x is less than or equal to 1. But there might be some more values restricted once we look at following through. So we have with r over q of x. Okay, so we have r of x all over q of x. Okay, so we have with r of x, okay, so you have negative 3x, and q of x, we had the square root of 1 minus x. Okay, so we got the square root of 1 minus x at the bottom. Okay, now r of x again had no restrictions, so that part is in the numerator. And you can have a 0 numerator as long as you do not have a 0 denominator. And just looking at what we have now with q of x in the denominator. Okay, all right, and so we have a twofold situation here. And because we have a radical, we have 1 minus x cannot be negative. So that's just reaffirming, x is less than or equal to 1. And also because we have the denominator consisting of the square root of 1 minus x, and since we cannot have a 0 value denominator, so you have 1 minus x cannot be 0. And so this is going to stress that 1 minus x, okay, again, it cannot be negative, cannot be 0, so anything left among the categories, we have that 1 minus x can only be positive. And so for the setup here, okay, so if an expression is positive, writing in terms of comparison to 0, okay, we're going to have greater than 0. And just for the follow through in terms of solving for x, so I can get the negative x by itself upon subtracting 1 from both sides. So I now have negative x is greater than negative 1, and expressing in terms of x itself. Again, if I change the signs, whether it's through multiplication or division, again, we're going to have the direction of the inequality to change. And so negative 1 times negative x, okay, so that will be x, and x in turn is going to be less than 1. Okay. And so this inequality will define what's in the domain, okay, for x. And so what we have here, so we have x is less than 1. Okay, so we have an open circle, and we're going to have ray moving continuously to the left and out in the direction of negative infinity. And so we're going to have for the domain of r over q of x. Okay, so you have going from negative infinity approaching but not including 1. Okay. So we have an open interval throughout. Okay, so far, okay, these are samples of dealing with the sum, difference, products, and quotient functions. Okay, working with 2 functions at a time. Now, there is another category of operations, and this will be what is referred to as the composition of functions. And for what we have regarding the composition of functions, and it's going to look initially like a set of product functions. And for what we have concerning, okay, the composition of functions, okay. Now, we're going to have one presentation, okay. Okay, you're going to have a composition, okay, and some might informally read this as fog x. Well, it's almost like the letter O separating the G, but it's a circle, and this circle symbolizes a composition, and this does not directly deal with multiplication. Okay, so you have this symbolism, and this is going to be read verbatim. F composed with G of x. And in terms of the operation, how compositions will work. Okay, so you have F composed with G of x, and we're going to have this is translated out to F of G of x. Okay, so the function whose letter is at the front, this is going to be on the outside, and the function whose letter is subsequent in the composition notation is going to be the interior function. Okay, so in this layout, okay, so you have G of x is the input function, and in the case of F, okay, so F is going to be the output. And if I reverse the sequence, I'm going from fog x to goth x. We're just doing the reversal. Okay, so with G at the front and F to follow, okay, this particular composition is going to be read G composed with F of x. Again, we have just operationally G composed with F of x. Okay, we have again a reversal in terms of what the input and the output will be. Okay, so by clustering together, okay, we're going to have that F of x is on the inside. So F of x is the input. And for G, okay, G is going to be the output. And let's say that in terms of how compositions might work. And we'll say, for instance, so if I were to determine F composed with G of x, and G composed with F of x, and we'll say that for the individual functions, okay, we're going to say that F of x is equal to x plus 2, and G of x we'll say is equal to 2x plus 3. Okay. All right. So for what we have here, okay, let me give just a bit of a visual, and I'm going to sort of drag this on out, and and this is for the purpose of just kind of like preparing once you get into the determination of the domain of compositions for, again, so we have for f composed with g of x, okay, so you have f of g of x. Okay, let me give you just a little bit of a visual. Okay, so you have f of g of x. Okay, now g of x is the input, f is the output. Now, if I were to follow through, okay, so we have f of g of x. Well, what do I do with g of x? Well, I treat it as the input that corresponds to the exterior function f. Okay, like have f of the input is equal to the input followed by the addition of 2. And likewise for f of g of x, okay, this is going to conceptually be g of x plus 2. Okay, now for what we have in terms of the specific expression, so you have f composed with g of x, so you have f of g of x, and specifying the input. Now g of x is going to be 2x plus 3. Okay, and so your 2x plus 3 is in reference to g of x, and so for g of x plus 2, this is going to be 2x plus 3 followed by the addition of 2. Okay, and there'll be no sign changes. So once I take out the parentheses, I got 2x plus 3 plus 2. And this will come out to 2x plus 5. Now, if I reverse the order, okay, so I got g of f of x and again, just kind of a visual setup. Okay, so you have like g composed with f of x. You've got g of f of x. Now again, the exterior function is g, and you got g of x is equal to 2x plus 3. Okay, so you got your leading function or exterior function as g, and you have 2 times the input plus 3, and with the input as f of x. Okay, so you're going to have conceptually, we got 2 times f of x plus 3. Okay, but now if I go ahead and identify the input f of x, and again, f of x is going to be at x plus 2. And so 2 times f of x plus 3, that's going to be 2 times all of x plus 2 followed by the addition of 3, and we have upon distributing, okay, so you have 2x plus 4 followed by the addition of 3. And so that's going to come out equal to 2x plus 7. Okay, so these are the compositions that we have here. So we're working with the same functions, but again, in spite of working with the same functions, how you sequence the functions, your compositions might end up being different. And let's say that if we have as case here, so first case we have with two linear functions, f of x and g of x. Now let's say that if I have one of the functions to be quadratic, like in the case of f of x is equal to x squared minus 3, and we have that g of x is equal to 2x plus 1. Okay, so we have in the setup, okay, so we have f composed with g of x I'll just mention, okay, so if I specify, go ahead and specify g of x. Okay, so I'm going to do something with 2x plus 1. So just, so if you try to create a bit of a visual structure, okay, so you have f composed of g of x, and we got f of g of x. Okay, now again, your exterior function is f, and f of any input is equal to the square of the input minus 3. And okay, so here we will be looking at the square of g of x minus 3, and with g of x at 2x plus 1, okay, in terms of the follow-through. So the input is at 2x plus 1, so we're now looking at the square of 2x plus 1 minus 3, and for f composed of g of x, so you have like 2x plus 1 times itself, so you have like 2x plus 1 times itself, so we have 4x squared, and the outside and the inside products will each be at 2x. We got plus 1, and then we have the subtraction of 3 to follow. And once we combine like terms together, so we'll have this trinomial as the output. So we're going to have 4x squared plus 4x minus 2. As for what we have in the case of g composed with f of x, okay, so you have g of f of x. So g is on the outside, f of x is on the inside, and again, f of x we have at x squared minus 3. Okay, and so to follow through in terms of g, again, you probably don't need the visual structuring, but just want to go ahead and mention for g composed with f of x. So I have g of f of x, and again, the exterior function, okay, again, we have g. And again, in terms of what to do with the function g, okay, we have g of the input is equal to 2 times the input plus 1. And with the input at f of x, 2 times f of x plus 1. But now with the input f of x specified at x squared minus 3, guess what? This will roll over to where we have 2 times the quantity of x squared minus 3, followed by the addition of 1, and then the follow through. So we're going to have 2x squared minus 6 plus 1, and we have with these functions, okay, we end up with g composed with f of x. Okay, this will come out to 2x squared minus 5. And okay, sometimes you might have the compositions. We have f in front of g, and also g composed of f to almost be the same, but for these particular outputs, in this instance, okay, they appear to be quite different. And now, just looking at what we have concerning the composition of functions, and tell you what, just case here of working with the determination of f composed with g of x and g composed with f of x. And we'll say here that okay, for f of x, we'll say that we have f of x is equal to 2x plus 4 and that g of x is equal to 3x minus 7. Okay, so in the next few moments, let's see what we get for these compositions. Okay, for these particular compositions, okay, notice, okay, for f composed with g of x, just kind of envisioning building blocks. Okay, so your outside function is going to be at f. Okay, and again, we have for the function f, again, you have f of the input is equal to 2 times the input plus 4. And again, we have with the input, okay, going over to g of x, okay, so you have f of g of x, okay, so that's going to be 2 times what we have for g of x, followed by the addition of 4, okay, and we have for f of g of x, okay, alright, now g of x is specifically, okay, 3x minus 7. And just continuing along the pathway of 2 times the input plus 4, okay, we have having specified the input, we're now going to have 2 times, okay, the input, we have x, g of x, and now we have specified for g of x, we have 2 times all of 3x minus 7, followed by the addition of 4, and distributing. Okay, so this is going to be 6x minus 14 plus 4. And finally we have 6x minus 10. And this will be the output, okay, we have for f composed with g of x. Now for the reversal, for g composed with f of x, okay, notice you have the leading function or the outside function to be g, okay, and the g function, okay, is defined where taking the input, we have 3 times the input minus 7. Okay, so again, g of the input is equal to 3 times the input minus 7, and with the input along the lines of f of x, we got 3 times f of x minus 7. So this is what we have in the general case, and then specifying what f of x is. So we're going to have g, and again f of x we have at 2x plus 4. Okay, so we got 3 times the input, 3 times the input. Once more, so you have with the input now at 2x plus 4. We have 3 times that binomial minus 7, and we have upon distributing, we have 3 times 2x plus 4, so this would be 6x plus 12. And then we have followed by the subtraction of 7. And we have for the output, okay, this time we have 6x once again, but a different constant to follow, where we have plus 12 minus 7, which will come out to 5. So f composed with g of x, well, that leads to 6x minus 10. We have in the reverse with g composed with f of x. Okay, this leads, on the other hand, to 6x plus 5. Right. And now, again, I sort of carried the extra verbiage out, so to speak, because we're going to sort of cross over to domain. Okay, we're going to have like focal points will be what we're going to have for the inputs and the output and how they can affect the domain. And in the case of the domain of the compositions of functions, okay, so for the domain of the composition of functions, and this will play by a somewhat different set of rules in comparison to the sum, difference, product functions, as well as the quotient function. Okay, and the domain, the composition of functions, will be formed by okay, so we have formed by combining the restrictions of the input function combine the restrictions on the input function and the resulting composition itself. And what you're going to have here is your focal points. In other words, you're going to keep the input and final answer real. Final answer as in the resulting composition. And just a case here, okay, and let's say we have two functions, okay, and say we're looking at determining f composed with g of x, g composed with f of x, and their domain. And we'll say that we have with our functions, we'll say that we have f of x is equal to 2x minus 4 and g of x is equal to 4x. Okay. So we have for the compositions. Okay, so I have f composed with g of x. Okay, so we're looking at f of g of x. Now I'm going to go ahead and specify what the input is going to be. Okay, and so we got, again, so we have you got your exterior function, okay, at f. So again, we have f of the input is equal to 2x minus 4, and f of the input g of x. Okay, so you got 2 times g of x minus 4. Okay, and with g of x specified as being exactly 4x, so this means we're going to have 2 times 4x minus 4, and we have, in this case, right, so you have 2 times 4x, okay, so this will be 8x. We have minus 4, and guess what? Okay, so the focal points have keeping the input and the final answer real. Okay, so the input is at 4x. No fraction, no even root radical. Input has no restrictions. Okay, and in terms of the final answer, okay, the composition itself, (8x minus 4). So this is a direct expression. And this also has no restrictions because you don't have an even root radical or a fraction or anything that causes any restrictions for the variable x. So what this means is that the input has no restrictions, final answer has no restrictions. So that means in effect we have no restrictions at all. So that means that, in effect, since there are no restrictions at all, that means that for the domain of the composition f composed with g of x, that's going to be the set of all real numbers. Okay, and for what we have, just taking the reverse. Okay, so we have with g composed with f of x. Okay, so I have g of f of x. And going ahead and specifying the input. Okay, so you have f of x is defined by 2x minus 4. And again, just in terms of what to do with 2x minus 4, again, we have the outer function at g. So again, we have g of the input is equal to 4x. Again, we have g of f of x, so that's going to be 4 times f of x. Okay, and again, with the input defined, okay, going from x to f of x to 2x minus 4. So we have 4 times 2x minus 4, and distributing. Okay, so this will come out to 8x minus 16. And once again, so we have with the input. Again, so you have no restrictions. Again, we have with the final result, once again, we have no restrictions. Okay, and since there are no restrictions between the input and the final output, or the final result, namely the composition, okay, so you have no restrictions at all. Okay, and so while the output is different, we still have another composition where we have no restrictions to exist, and we're going to have the domain to also end up as being the set of all real numbers. So we've got all real numbers throughout, okay, for these. And we'll squeeze this in right fast. And we'll just go with the first composition. Okay, so if I have determined f composed of g of x and its domain, and we have given, okay, so we'll have f of x is equal to 1 over x minus 3, and g of x is equal to x minus 5. So we have, in the case of f composed with g of x, so we're looking at f of g of x and g of x, we have x minus 5. Okay, so again, the output function is in accordance with f. So f of x, and 1 over x minus 3, and f of g of x, okay, so you have 1 all over g of x minus 3. Okay, but with the input specified at x minus 5, we'll have 1 over, you got x minus 5 minus 3, and we have for the resulting composition, so you got x, and negative 5 minus 3 is going to result as negative 8. So that will be the final composition. So we have 1 over x minus 8. Now again, we have with the input, you just got a linear expression, so the input has no restrictions. So we have here, oh, thinking of the other one too fast. Okay, so the input has no restrictions. This one use NR, no restriction. And for the final result, okay, you have 1 over x minus 8. And x minus 8 is in the denominator position. The denominator cannot be 0, so x cannot be at 8. So the input has no restriction. However, the final output disallows 8. So the only restriction between the input and the final result is going to be the x cannot be equal to 8. So 8 is going to be left out, but everything else, okay, before and after it, will be in the domain. And so it's going to follow that for this domain. Okay, so we're going from negative infinity, approaching but not including 8. That is for the first half. And for the rest of the domain, it's going to be the set of values x greater than 8. And so we're going to have parentheses throughout.